In this video, I'll show you how to design for 3D printing. We'll take this gantry that I designed and improve it step by step in strength, tolerances, printability, and visual appeal. The tricks and methods shown here can be applied to any model in any CAD program. I'll guide you through my workflow and share my learnings from designing 3D printed parts for this robot. Welcome to JanTec Engineering. Thanks to VOXELPLA and Prusa Research for supporting my channel. Prusa supports me with my studio, so I can create all these videos. Designing something to be manufactured comes with different sets of rules. While injection molding requires draft angles for part ejection, fillets are needed when CNC machining due to the round drill bits. 3D printing offers more freedom, yet it comes with other boundaries like the anisotropy of finished parts. This means that the parts have different mechanical properties in different orientations due to the layer stacking. That's one of the main things that needs to be considered when designing for 3D printing. And that's exactly what I want to explain to you in this video. We'll turn this sketch into a simple 3D model in Fusion 360 and then improve it step by step for 3D printing. Of course, everything shown here can be applied to any design in any CAD program. So, when you start designing something, you might or might not have your own workflow yet. While designing parts for personal projects and a recent robot competition at university, I found a way that works well for me, but there are certainly other approaches that might work better for you. Anyway, in this video, I'll follow an iterative process, starting by defining a MVP, which stands for Minimal Viable Product. This is the simplest functional version that does the job. Then, this design gets improved with each iteration in different aspects like strength, tolerances, and printability. Especially for beginners with little experience, it's helpful to actually print out some test pieces or prototype iterations to get a feel for dimensions, required clearances, and other potential issues. The more experience you get, the fewer iterations are needed. While this approach is extremely useful for beginners as it provides direct feedback, there are other opinions on this. Christopher Helmke, who designed 3D printed screw counting automations, has a really interesting take on this that I didn't want to leave out. Luckily, he's located in the same industrial complex as me, so let's ask him real quick.
Okay, so my take is that you should do it completely different to Jan's approach, which is that you should try to make it first try, so only a single iteration. And in my opinion, that's right because 3D printing is much too slow to be part of a thought process. The main benefit, or the actual benefit about 3D printing is not that it doesn't have a lot of manufacturing constraints or anything, but that it's low cost and thereby accessible to lots of people. But there's also a big danger in that, and that is that you will start to print very, very fast. I actually don't like using 3D printers for my creative process because of that. And the reason for that is that if you start to print something, then you will stop to think about it. And you need a long thinking process about any part to actually get a complex design to work. And if you always stop in between for 2 hours at least to wait for the print to finish, then you will never get any complex system to work, in my opinion. And the second reason for that is that you need to have like very strong assumptions about how something is going to work to then test them. So the print that you will get out will not have any meaning to you if you have not put a lot of thought and work into it, and you will not improve your design whatsoever how many iterations you do. Actually, I claim you have only like creative energy for like 5 iterations in you, and after that you're done. So don't waste them on useless stuff.
So, take the whole process shown in this video with a pinch of salt. Try to resist the temptation of hitting print immediately after designing and take some time to really think through the model first. I needed a gantry for the x-axis of a low-cost robot that plays Jenga, but more on that in another video. For this part, I have a few specific requirements: the outer dimensions, fixing points, the rods it needs to glide on, and the belt attachment. To start, I did some research on similar designs, took some notes, and made a few drawings on paper. I then transferred those ideas into my CAD program using simple sketches and extrude operations. What I ended up with was a basic blade with cutouts for the 2 rods, holders for the belt, and a couple of holes for attachments. Now let's print our MVP and see if it actually works. Well, it does hold the belts. The rods don't fit perfectly, but with a little drilling they should be fine. The holes for the screws are a bit tight, but it works. I don't like the sharp corners and overall feel of it. I mean, it looks like a block with a couple of cutouts, probably because it is a block with a couple of cutouts. I wouldn't call it a good design, but keep in mind, we never wanted a good design. We wanted an MVP, something that proves the concept and motivates us to stick with the idea and improve it further. We can now take this physical prototype to make a list of things we want to change in the next iterations. Let's start with strength. We have to ask ourselves, where does force apply to our object? In FDM 3D printing, parts are anisotropic, meaning they have different mechanical properties depending on the direction of the force relative to the layer lines. Because of this, it's usually good advice to look at the fixing points and try to bend your prototype in different orientations to find the weak spots. In this design, there's really only one critical spot: the pins holding the belts. Because of our print orientation, these are standing in the Z direction, which is the weakest orientation of any FDM print. If you pull on the belts, it applies lateral force, making them very likely to snap right along the layer lines. Even if they might not break during normal use, we have to account for user errors, like over-tightening the belts during assembly. One easy way to solve this is to use hardware, in this case screws for reinforcement. I actually did a dedicated video on this channel about incorporating hardware into 3D prints to make them stronger. I picked these M2.5 screws from CNC Kitchen and took some measurements. Back in CAD, I first subtracted the length of the screw's head by selecting the faces and extruding them by that negative distance. Then I created a sketch to create holes for the screws to go in. To make the screws compress the layer lines, the holes should be tight. About 2.4 to 2.5 millimeters for an M2.5 screw works best. For demonstration, I made a sample model with 3 pins. The first is a regular pin. The second has a fillet to increase the surface area at the base, and the third is reinforced with a screw. The regular pin breaks easily with very little force. The fillet pin takes more force but eventually snaps at the smallest section. The reinforced pin, however, is almost impossible to break. The screw keeps the layers clamped together and it holds its shape perfectly. Now we can apply this to our design and print the first iteration. The screws go in as intended, and now it's time to adjust the dimensions for a better fit of the rods. Before we continue, a few words about the sponsor of today's video, VOXELPLA. If you've been following the channel, you've probably seen me using voxel filaments for most of my projects. They offer high-speed PLA Plus and PETG Plus in a huge range of colors. I really value the reliability, toughness, and high-speed printing capability. Starting at just $16.99 per kilogram, it's really affordable too. For print farms, voxel filaments are an ideal solution with additional bulk discounts available. Beyond the filament, Voxel also offers a variety of printer upgrades like the Hula anti-vibration feed, X-filter, anti-bento box and vento filtration systems for bamboo lab machines. They are great for improving your print quality and making your workspace a bit safer. All products are made in the USA and are tested 24/7 in their 250 machine print farm in Southern California, ensuring real-life reliability. If you want to try out the filaments or get some upgrades for your printer, you can get free US shipping on orders over $75 plus for a limited time you can take 10% off orders over $100 by using code JanTec10 at checkout. Thanks again to VOXELPLA for supporting the channel and making this video possible. Let's continue with dimensions. Because there are variations, or tolerances, in both our 3D prints and the hardware we're using, we have to design with clearance in mind. As a starting point, I usually aim for 0.15mm to 0.2mm clearance for holes to achieve a rather tight fit, while 0.3mm or more is better for parts that need to move or glide freely. However, these values aren't fixed. Every printer and material behaves differently, so it's a good idea to download and print a tolerance test board from sites like Printables. This gives you a physical feel for your specific setup. For some hardware, like the heatset inserts from CNC Kitchen, you don't have to guess, as they actually provide recommended design dimensions in the documentation, which takes a lot of the trial and error out of the process. In CAD, I added a clearance of 0.3mm for the screw holes and 0.4mm for the horizontal rod holes. Now there's a pro tip. I didn't just type these numbers into the sketches. I added them to the parameters list in Fusion 360. By defining parameters like clearance tight or clearance glide, you can assign these values throughout your entire project. If you finish a print and realize the fit is a bit too loose or tight, you don't have to go back through dozens of sketches. You simply change the value in the parameter table once and the entire design updates automatically. In theory, everything could be a parameter, but for most simple designs, I keep it minimal. Let's print this iteration and see how we did. The rods now slide through with just the right amount of resistance and the screws fit perfectly. However, looking closely at these horizontal holes, they aren't perfectly round like we modeled them in CAD. The top of the circle is slightly drooping. Fixing this leads us right to the next chapter, printability. When it comes to printability, one of the main goals is to avoid support structures. It saves material, reduces print time, and eliminates tedious post-processing. There is a good rule of thumb here. Most printers can handle overhangs up to 45 degrees without needing an extra support. This is where our drooping holes from the last section come in. If we simply increase the clearance to compensate for the drooping top, we end up with an oval-shaped hole that doesn't actually provide a good fit for a round rod. That's why it's a good idea to use a teardrop shape instead of a simple circle. By modeling the top of the hole with a 45-degree angle, the printer can bridge the gap perfectly without any sagging. Here's my workflow for this in CAD. I start by drawing two lines tangent to the top of the circle. I constrain the endpoints where they meet to be vertically aligned with the circle center. Then I dimension the angle between one of those lines and the horizontal to 45 degrees. This fully defines our sketch and ensures the printer can handle the bridge. Because this is more precise, we can actually lower our clearance here by 0.1 mm compared to a standard round hole. I also use this iteration to add some functional chamfers. Specifically, I added lead-in chamfers for the belt paths and screw holes. These act like a funnel, making it much easier to guide the components into place during assembly. Plus, chamfers are a great way to hide the natural roundness of sharp corners caused by the circular printer nozzle. Finally, I added a small chamfer to the very bottom of the part to compensate for elephant's foot, that slightly squished first layer. Let's get this final version on the printer and see the results. The rods and screws fit with only minimal play. We have a perfectly functional gantry now. Now that our part is strong, the holes are the right size, and it prints reliably without supports, there's only one thing left to do: improve how it looks. And honestly, depending on what you do, you might just skip the step, and that's fine. But keep in mind, whenever you show the design to someone, publish it online, or even just look at it yourself during assembly, you'll probably appreciate it if it looks a bit more interesting and unique. I have to admit, I'm not an expert in aesthetic design, but I do appreciate well-thought, minimal and interesting design. I love thumbing through the complete works of Dieter Rams, for example. For design noobs like me, there are some simple yet effective tricks to make almost any part more visually appealing. Rounding off sharp corners and using chamfers and fillets. I think it fits well within the whole design language of the robot. Afterwards, you might want to consider some post-processing like sanding, painting or chemical smoothing. I actually covered this in a previous video, so feel free to check that out if you want a smooth finish. Well, that's how we got from this, our MVP, to this, a functional, minimalistic design that fits perfectly and does the job. This iterative approach is exactly how I design most other parts of the robot, like this axis, which uses a 3D printed rack and pinion gear system. I started with manual prototypes to dial in the dimensions and then integrated the motor and end stops to the final design. I hope this video gave you some useful insights into my workflow and how you can optimize your designs for 3D printing. I'm really curious to hear about your workflows and personal tricks, so let me and the rest of the community know in the comments. As always, a huge thanks to my channel members and to all of you for watching. See you in the next video here at JanTec Engineering.